Hey everybody, how's it going? I'm just sitting here in my car, stuck in traffic, and been really thinking about complexity a lot lately. The role it has in software development, the role it has in systems in life, and everything that we interact with on a daily basis. And a couple really startling things have been jumping out to me lately. As you may know, I've been working on building a 8-bit computer for the past couple months. I'm starting off on breadboards. I've got it complete on breadboards, and now I'm working on transitioning it from breadboards over onto permanent PCBs. It'll still have the breadboard look and the breadboard feel, but it'll be more modular, so it'd be easier for me to transport. I could actually ship it places, use it in real conference talks, let people interact with it, etc. Because one of the reasons that I built it was to better understand computers, and if I can better understand a computer, then hopefully I can help others better understand it as well. But so, one really interesting thing jumped out at me while building it. Every component of the computer is actually simple. And when I say simple, I mean I could explain one of the components to you in a few minutes. We're not talking about a lot of detail. We're not talking about, really difficult systems. Every one of these components at its root is really simple. The problem is twofold. One, there's a lot of these things, right? There's lots and lots of different components on my current computer, the current iteration of it. I've got somewhere in the neighborhood of 35 different modules that all plug together to make the computer work. Definitely not simple. And when you look at the end result, you get this incredibly powerful thing at the other side. But how does one ladder into the other? I'm reminded of Douglas Hofstadter's book. I don't remember whether it was Gödel Scherbak or Through the Mind's Eye, but one of his books, he talks about this phenomenon of emergent behavior where you have something like a group of ants. Each ant by themselves doesn't really contribute much in terms of knowledge. In fact, the ant has a single neuron. It doesn't contribute thought the way we think of thought, symbolic behavior. But instead, what winds up happening is, by themselves, the ants are stupid. But when you get enough of them together with the right chemical mixes, you actually wind up in a situation where you have this emergent design where you actually have colonies of ants that behave as a single organism. Same exact thing happens with computers. The computer you're watching this on is nothing more than a whole metric fuckton of PN junctions of transistors, but actually even lower level than transistors, silicone touching silicone that are doped differently. And because of how they're doped, and because of how they touch and they're arranged, these very simple things wind up having this enormously complicated behavior. But how does that apply to software development? Because ultimately, those two examples I just showed are completely hardware. It's this notion of necessary complexity versus unnecessary complexity. A lot of conversation has been had around this notion that complexity is bad. We need to simplify. Dirkstra's famous quote, I would have written you a simpler letter, but I didn't have the time. I think it was Dirkstra. I would write you a simpler letter, but I didn't have the time, where we value the trade-off of complexity, but simple is always better. But is simple always better? When we complicate systems, we give them new behavior that did not exist in other forms. And what I mean by that is, when we have a very simple system, so something like BASIC, the basic programming language, it is so simple that you can build pretty much anything, but to build anything complex is kind of a pain in the neck. And then you build up on top of that, you build something like C, the C programming language, where it's really hard to build anything complicated because managing the memory by yourself is really this difficult problem. And a lot of people do it. There's a ton of C code out there in the world. But it's not easy, and it's not easy to do well. But when we build on top of that, we're able to build something like a Python or a PHP, Ruby, etc., where we use this simple base that would be too difficult to write anything really of major note, to build another layer of simplicity at a higher abstraction level. And this is actually an awesome thought when you start to think about it, and when you sit down, because you wind up in a situation where adding a little bit of complexity actually makes things simpler at a different perspective level. So when we rally against complexity and we say, complexity is the root of all evil, it's no, complexity is not evil. Complexity is not bad in any way, shape, or form. In fact, we need complexity, because complexity, if done right, will bleed simplicity at a higher level. Let me give you another example here, and this actually I think will illustrate this point of levels. A game of pool is inherently very, very simple. In fact, most first-year college-level physics students can perfectly model the game. Even some high school students can model the game. You have these perfect spheres that impact each other. You can predict the angles that it goes off, so it all just becomes down to force and angles. And a little bit of friction if you really want to get fancy. But when you look at the real world, that doesn't quite hold up, because it doesn't model what's actually going on underneath. What's actually happening is infinitesimally more complex. You have tons of different atoms. Each one of those atoms interacts with the ones next to it. So you have the atoms in the pool ball, the atoms in the felt, the atoms in the slate, and they're all subtly interacting differently. So this concept that we have of the perfect idealized pool ball is really just an abstraction over a simpler system built infinitely more complicated. And we're just looking at the simplified projection when we look at the pool balls on the pool table. What I'm suggesting here is the exact same thing with software. The complication is not only a good thing, complication is exactly what you want. As long as, a little bit of acceleration on the tool. So the complication is actually what you want, but we don't want unbounded complication, because when you have this complication going crazy, you wind up with this rat's nest. But if you can somehow figure out a way to organize that so the higher level is simpler, and so so if you can organize it so the higher level abstraction level is simpler, this complicated code actually serves a meaningful purpose. And I think where we get into trouble is when we try to prevent that higher level abstraction from materializing, because that middle layer becomes more complicated when you do that. This is a common criticism against dependency injection, because by nature, dependency injection is going to increase the complexity of code. Increases the number of parameters that you have to have, and increases the number of moving parts in the code a little bit. But the point is, it actually reduces the local complexity when you look at that item, because now you don't need to think about all of these moving parts. You can focus on the area that you are working with. And that's where I think the really, really fascinating part comes in, because you have all of these competing issues, right, with complexity. On one hand, you have as simple as possible, where you're trying to make it easy to understand. But at what level do you make it easy to understand? On a 100 million line code base, it's difficult to understand no matter where you are in there, because it's just a big system. But you're also trying to trade off between local complexity and global complexity. Dependency injection is a technique for trading local complexity, meaning I want to make my local scope, my class scope, or my project scope. Not project. my package scope smaller, meaning pull the dependencies out, I don't even want to think about them, but at the cost of making your overall global scope a little bit bigger. Not much, but a little bit. So that balance between local scope and global scope is, I think, where all of the fascinating components to software design come in. We can sit down and talk about all until we're blue in the face, how the different techniques and what benefit we're actually going to cause ourselves, etc. But I think the really interesting thing here is having the conversation. Too often we're sitting down going, well, complexity is evil and we must eliminate complexity. And in fact, you hear framework authors coming out and saying we're simple, we're easy to understand, we're easy to use, and using complexity as this gigantic negative. In reality, I think it's a lot more nuanced. I'm not saying that they're wrong. Complexity does have its place, and there is room for simplicity, and simplicity is a very, very valuable thing. But when looking at the way we write software, I think it's ingenuous to ignore the complexity side and the benefits complexity can give you. And I'm not saying just make your code base as complex for the sake of it, but what I'm actually saying is, why not just try to understand the different effects and the different pulls and pushes that are affecting your code base. Try to understand that there's many different levels to look at your code base at, and not all of them are necessarily bad. I think it's a fascinating topic, and I think, to me at least, it's one of the bigger questions that's left out in modern software engineering, because we seem to have a lot of these philosophical debates between things like functional and object-oriented and state versus immutability versus naming conventions, and a lot of it is bullshit. If you're effective in a programming language, you're effective in a programming language. It doesn't matter whether it's functional, OO, procedural, whatever. Where we can start to get into trade-offs is when we can start to bring technologies in to help us, more advanced compilers, etc., when we can start to make assumptions about code. But also when it comes down to reading and understanding code, there's massive difference between some of these paradigms. But we only talk about the one side of it. Which is the invariance, which is how hard it is to understand. And people don't really look about how hard it is to understand on that level. I don't know. I think complexity is a fascinating topic. Let me know what you think. And if you like this format of my rants while driving, and if you do, maybe I'll do some more of them. All right, thanks. Bye.